Yeah, good morning my dear students. Today we are going to discuss about the topic on flame atomizer. What is this flame atomizer? The flame atomizer is a very important component of atomic absorption spectrometer. The flame atomizer is also called as nebulizer burner system or premix burner system. So when we talk about the flame atomizer, first of all we should know what is the light source used in flame atomizer. One of the important light source used in atomic absorption spectrometry is hollow cathode lamp, and the other one is electrodeless discharge lamp. So today we are going to discuss about the construction and working of hollow cathode lamp. The hollow cathode lamp, basically this is the construction of the hollow cathode lamp. If you look at this hollow cathode lamp, we have the inner cathode, the hollow cathode, which is basically made up of iron as an element, and this is hollow cathode is filled with some inert gases such as neon or argon at a pressure of 130 pascals, right? And there is an insulating disc, there is a quartz window here, and this is covered with an anode. The hollow cathode is covered with another side with an anode. So there are different elements over here. Suppose for example, if you want to analyze the element iron, then we have to use iron as the cathode in hollow cathode lamp. If you want to analyze lead as an element in atomic absorption spectrometer, then we have to use lead as a cathode in hollow cathode lamp, right? So same element we have to use in the hollow cathode lamp. So different hollow cathode lamps are available for different types of elements. Now, why we are using this monochromator? Because monochromator cannot isolate the lines narrower than 10 power minus 3 to 10 power minus 12 nanometer. The very important thing, monochromators cannot be used to narrow the lines between 10 power minus 3 10 power minus 12 nanometer. Therefore, hollow cathode lamp is basically used. That is the reason we are using hollow cathode lamp. Now when we talk about the cathode is, as I told already, is made up of iron as an element, and the filler gases argon or neon. Now the first step, there are three steps in this working of this hollow cathode lamp. In the first step, what will happen? I apply the potential between the positive and the negative terminal. When I apply the voltage between these two terminals, what will happen? The filler gas will get ionized. The filler gas is argon, which will be just ionized into argon ion and electrons. Now in the second step, what will happen? The positively charged argon ions will try to strike towards the cathodic terminal. Right? They will be attracted towards the cathode. In the cathode, the ion element is present. So what will happen? These argon ions will try to make the ion element into ion or sputter them as a metal atom in the gas phase. They will convert the ion into ion metal atom in the gas phase, right? So first mechanism is sputtering mechanism. Now once sputtering takes place, after that what will happen? This excited ion atoms, then they will go for vaporize and they will emit the light radiation with the same frequencies that are absorbed by the sample ion atoms to the flame. This is a very important step. What will happen? These ion atoms, this will be there in the gas phase, so they will go to the excited state after vaporization, then they will come back to the ground state. So they will, what happen? They will, when they go to the vaporized state by excitation, then after that when they come back, they emit the light radiation with the same frequencies that are absorbed by the sample ion atoms to the flame. That means in the sample, if the ion atoms are present in the sample, if I keep the ion atoms in the sample, so here from the hollow cathode lamp, whatever the ion atoms wavelength which is emitted light radiation will be coming, that should match and that will be in resonance with the ion atoms present in the flame during the flame atomization step. So this is a very important aspect. So what will happen? These ion metal atom which is in the gas phase will react with the electron, right? It will try to react with the electron and they will go for excitation. So the ion atom in the gas phase will be going to the excited state, and upon emission what will happen? They will come back to the ground state, right? Gas phase. Along with that they will emit the light radiation of a specific wavelength, and this wavelength whatever is emitted, right? So this wavelength is coming from the hollow cathode lamp. This is from the hollow cathode lamp, right? Is it clear? This is from the hollow cathode lamp. From this light radiation is coming, this wavelength is coming here. At the same time the sample also is having the wavelength. The sample also is having the wavelength, right? So what will happen? The excitation wavelength in the sample and the emission wavelength from the lamp, they will be in resonance with each other. So this is the major mechanism here, especially that is why the hollow cathode lamp is very, very important aspect, right? Now when we talk about this nebulizer burner system, it is also called premix burner system. So this is the construction of the premix burner system. So we have the basically we have a mixing, that is your, this is basically a burner head. There is a burner head here. Basically we are having the sample here. The sample will be present at this spot. Okay, we will be having the sample here. So from the sample, it will be taken into the help of nebulizer. So nebulizer system will be present. And here we will be adding the fuel as well as the oxidant. Then there is a glass bead here. They will mix it up, all these things together. Then they will go to the baffles. Baffles also will try to mix it up and making it into a very tiny droplet. Then everything will be mixed in the mixing chamber. This is the spray chamber and this is the mixing chamber. From the mixing chamber, it is attached with the burner head, and from the burner head, it is going and giving the flame as such. So this is the general construction of the nebulizer burner system, which is also called as flame atomizer, or simply we call it as pre-mix burner system. Pre-mixing we are doing. What is called pre-mix burner system? So I will divide this entire chamber into three areas. One is the mixing chamber, another one is the burner head, and the third one is your nebulizer. The mixing chamber is basically this one. The mixing chamber is basically made up of stainless steel, casting lined with plastic to avoid the corrosion effect. Now if you look at the burner head is the top portion. The burner head is made up of titanium, which can withstand the very high temperature. For example, acetylene air mixture will be having 2400 to 2700 Kelvin. And the third important component of the nebulizer burner system is your nebulizer. Particularly nebulizer is in the lower area. The nebulizer creates the aerosol from liquid sample. Aerosol, you know, very tiny mist of air droplets, and maintains the sample uptake rate of 1 to 5 ml per minute. So this is all about the construction of your nebulizer burner system. Now what is this fuel oxidant mixture? How much fuel we should add, how much oxidant we are using. So basically the fuel oxidant mixture, what type of fuel we are using, what type of oxidant we are using. These are all the commonly used fuel oxidant mixtures. Acetylene air is the most commonly used fuel oxidant mixture, which can withstand the temperature up to 2400 to 2700 Kelvin. And most of the, mostly for analysis of 30 elements we are using acetylene air mixture. The second important fuel oxidant mixture is acetylene with nitrous oxide. Temperature ranges from 2900 to 3100 Kelvin. Especially for a high temperature for metal, where the especially metal form the metal oxides like aluminum and titanium. And the path length of this particular flame fuel oxidant mixture is 5 centimeter. We can also use acetylene oxygen mixture, which is capable of withstanding the temperature from 3300 to 3400 Kelvin. We can use hydrogen air as a mixture ranging from 2300 to 2400 Kelvin, and hydrogen oxygen we will be using from 2800 to 3000 Kelvin. And cyanogen oxygen flame we are using at 4800 Kelvin, especially from the emission of calcium atoms. So cyanogen oxygen flame is used for a very high temperature of 4800 Kelvin. So this is all about the flame composition, right? Now what type of flame we are using basically? This is also another important thing. We are using two types of flame. One is called rich flame, another one is called lean flame. Rich flame is rich in fuel. Suppose if you are using 80% of the fuel and only 20% of the oxidant, then it is called rich flame. Okay, rich flame is rich in fuel. What is the purpose of the rich flame? The rich flame will reduce the excess carbon. That means the rich flame means carbon content will be more. So that excess carbon will reduces the metal oxides and hydroxides, and therefore increases the sensitivity to the flame. This is the purpose of rich flame. Whereas if you take the lean flame is an oxidant rich flame, and it is a much hotter flame. Right? Here the oxidant will be more, air will be more 80%, and acetylene will be very less, for example. Right? So that is the purpose of lean flame. Depending upon the technique or what type of fuel we are using, accordingly we have to use, whether we have to use rich flame or lean flame. It depends upon the percentage composition of the fuel oxidant mixture. Right? Now the other important aspect is a flame profile. This is also another interesting area. Flame profile means, if you look at that from the burner head, initially you will get the blue cone, which is the primary reaction zone. After the blue cone, that is before the blue cone, there is a preheating region. Then you will be having the blue cone. Then after that, after the blue cone, you will be getting the outer cone. The outer cone, the original combustion takes place. That is the secondary reaction zone is the outer cone. And between the blue cone and the outer cone, there is an interconal layer. This is also there. Okay. So what will happen? The gas enters the preheating region from the burner head, right? And it is heated by downward conduction and radiation from primary reaction zone. Okay, the mechanism is downward conduction and radiation. These are the two important mechanisms, downward conduction and radiation from the primary reaction zone, which is the blue cone. And combustion takes place or completed in the outer cone region, right, where the surrounding air will be drawn into the flame. You can see here the surrounding air also will be captured along with the flame. That will leads to the combustion of the flame, right? So therefore, whenever you want to originally find out the analyte signal, you have to subtract this whatever the air will be drawn into this outer cone layer, that is your outer cone layer, that you have to subtract it, then only you will get the original sample signal, right? Now the droplets, what they will do, the droplets will enter the flame, they evaporate. Once they evaporate, you will be getting remaining solids, and the remaining solids are vaporizing, and then they decomposes to atoms, right? So this is how the flame profile is basically working. The flames emit light, and the total analyte signal that must be subtracted from the total sample signal. As I already told, any outer air will be there, that will be joining with the flame, and they will also go for the combustion. So therefore you have to subtract those outer air which is entering into the original sample signal. Once you subtract that, you will get the original sample signal, right? So this is all about the flame profile, right? Now what is an advantage of this flame atomizer system or the nebulizer burner system? The very important advantage is it provides a very long light path, number one. So when it provides a very long light path, there is a little danger of incrustation. You can see that safety will be much better, right? Because from here we are putting the sample, it is going and finally it is going here, right? So there is a little danger of incrustation if you have a very long light path, right? This is one of the advantage. And then the major disadvantage is if more volatile solvents are evaporated preferentially. So we are using the mixture of solvents, but what will happen, more volatile solvents are preferentially getting evaporated. So in that case, you should be very careful. If you are using more volatile solvents only here, so that will go for burning explosion also. Therefore, you should be careful, use the mixture of solvents here, right? So this is one of the disadvantage. And 5 to 15% of the sample reaches the flame. Say if you put 100% of the sample, finally hardly 5 to 15% of the sample maximum will try to reach the flame, right? Somewhere they will be getting lost here, and finally the concentration going into the flame will be lesser, right? So that is the problem. In atomic absorption spectrometry, we have to measure the concentration of the metal atoms, right? If you put 100% of the sample, hardly 15% of the sample reaches the final flame, then the concentration measurement will not be accurate, right? So that is why in olden days they have used this for atomic absorption spectrometry, but in modern days we are going for graphite furnace, right? So this is the major drawback of this flame atomizer or the nebulizer burner system, right? And one more disadvantage is also there. The viscous samples like oil and blood sample, they require wet ashing or dilution. That means when you want to analyze the viscous samples like blood sample, serum sample, or any urine sample, or if you want to analyze this particularly this oily samples, then we cannot directly send it into the atomizer or the flame atomizer as such, right? You have to do some pre-treatment, then you have to send it over there. So what type of pre-treatment? You have to do the proper dilution for the wet sample, or you must go for some pre-treatment procedures like wet ashing, right? Wet ashing procedure you have to do, then you can subject it into the flame atomizer. Then only it will give the proper results, right? So conventionally in the olden days, they have used this flame atomizer or the nebulizer burner system for both atomic absorption spectrometry as well as for atomic emission spectrometry. But nowadays we are not using this. As I told, the concentration of the sample reaching the final flame will be very less. So it will not give the accurate result when we calculate the concentration and indirectly coincide with atomic absorption spectrometry. It is not possible. That is why we are not using and relying upon this technique nowadays. So this is the only technique used for both atomic absorption and atomic emission spectrometry. But as on today, modern particularly in the modern instruments, we are using graphite furnace for atomic absorption spectrometry. Whereas the same flame atomizer can be used for flame photometer or flame that is particularly for the atomic emission spectrometry. We can use this as a model. Still now we are using this as a model. Okay. So this is the difference you should know in mind, especially when you are studying this particular topic, right? Because it's a very vast area. One should remember what are all the key points over here. That is very, very important, and to discuss in the class, to remember all those aspects. Thank you very much, my dear students. Thank you very much.